Hello, this is the lecture for relations versus functions, the last section in Unit 1. All right, so if we start at the beginning, we should define a relation. A relation is a correspondence between two sets. One of the sets contains all the possible inputs to the relation, and the second set contains all the possible outputs of the relation. All right, here's an example here. In this diagram, we're looking at the relation that identifies the number of representatives in the House of Reps for each state. All right, we can see that Alaska has just one rep in House. Arizona, though, has 9. California has 53, so on and so forth. So this relation, and it's just presented as a diagram, this relation relates the number of reps in the House to a state. So the set of all possible inputs to a relation is referred to as the domain, and the set of all outputs of a relation is referred to as the range. So let's look at a couple of examples here of relations. A specific type of relation called a function is one in which each element of the domain, each input, corresponds to only one element in the range or the output. So, and it corresponds to only one element in the range. So if we look at these two examples here, could we say that they are functions? Well, let's see. This first relation relates animals to their life expectancy. All right, so a dog's life expectancy is 11 years, a kangaroo is also 11, a duck's life expectancy is 10, and a rabbit's life expectancy is 7. Okay, is this particular relation a function? Well, to determine if it's a function, we have to ask ourselves, does each element in this domain correspond to only one element over here in the range? Remember, our inputs are the domain. Our inputs, or our starting point, is the domain. Our outputs are the range, or our ending point is the range. Well, let's see, dog only has one life expectancy. Duck only has one life expectancy. Kangaroo has the same life expectancy as dogs, but it still only has one. And a rabbit only has one. So we would have to say that this relation that relates animals to their life expectancy is in fact a function. If we look at the second example over here, this relation relates phone numbers to people, or relates people to their phone numbers. Okay, Dan's number is 555-2345. Gizmos is here. Colleen has still has a landline, right? Colleen has 2 phone numbers, so she has a landline and a cell phone. Phoebe, however, just has 1. So this second relation here is not a function because each element of the domain, the inputs, each element of the inputs of the domain does not correspond to only one. Colleen has 2 phones, so it violates the rule for a function. So I'd have to say that this one is not a function. And again, it is not a function because there's an element in the domain that corresponds to 2 different elements in the range. Okay, functions can be represented multiple ways. We can represent a function as a set of ordered pairs, and in this first example here. These ordered pairs, the first value usually refers to the x coordinate if we were plotting points, and the second as the y. It doesn't necessarily have to be that. A second way to represent functions is algebraically. This is a more powerful representation of a function, because if we're just looking at ordered pairs, I only know the output that goes with the specified inputs. So if the input is 1, I know the output is 1. If the input is 2, I know the output is 4. Or if I have the element of 3 in the domain, that's an input, right? That will correspond to the element of 9 in the range. That would be the output that goes with 3. But I only know about these 3 sets of inputs and outputs. When I represent a function algebraically, this tells me the rule that defines the function. Okay, so function notation here, f of x, this means this function is called f. It's accepting some value for x as the input, right? X is going to be the input, and the value that we get out of it, or the output, is going to be whatever that input is squared, right? So if the input is 1, as it was up here, the output is going to be 1 squared, or 1. If the input is 2, the output is going to be 2 squared, or 4. If the input is 3, the output is going to be 3 squared, or 9. Okay, so looks like these are the same function, but this algebraic representation is far more powerful, because if the input is 1.5, for example, I can pick any input I want. I know what output that input corresponds to, because 1.5 squared is 2.25, right? More powerful when we have the algebraic representation of a function. But we can also represent a function as a table of values. Okay, here we've got some inputs or some x's that correspond to these outputs or these y's. Okay, we have 1 and 2 here. We don't have 3, but we've got some other ones. Looks like it's still the same function, huh? Potentially. Tables of values are also limited, like ordered pairs are. They don't tell us about all the inputs. They only tell us about the ones that are given. A fourth representation for a function is graphically. This is also a very powerful representation, because given any input, I can find the output, right? This is showing me, a graph is actually showing me the set of all ordered pairs for a function, right? The set of all ordered pairs. So any x, I can find the y that x corresponds to by finding that point on the graph. All right, let's look at a few examples. Let's look at a few examples. Here we have a relation that's being represented as a table of values. It might be that same one we were looking at. I think that was the squaring function. It looks like it. Couldn't be sure, because we only know about 1, 2, 3, 4, 5 inputs, right? But for this function, it's a table of values. We're to state the domain. What is the domain here? Well, the domain is the set of all possible inputs here. And typically, the inputs are going to be the x. That's typically the independent variable, right? So this domain is going to be 1, 2, 3, 4, and 5. Okay, and then the range refers to the outputs, right? Outputs are usually the y's, right? Or the dependent variable y. The value of y is dependent on the value of x, the independent variable. So the range for this particular function then is going to be 1, 4, 9, 16, and 25. Okay, is this example, this relation, is this actually a function? Or is y a function of x? Another way to say that. Well, does each element of the domain, remember our inputs, our x's are typically the domain, does each element of the domain correspond with only one element of the range? Well, 1 corresponds with 1, 2 corresponds with 4, 3 with 9, 4 with 16, 5 with 25. We don't have any repeats there at all, so I would have to say that yes, y is a function of x here. How about this example? Well, the domain's going to be all my x's, right? So 1, 2, 3, -2, and -1. Okay. The range is all my y's or all my outputs. So the range is 1, 4, 9, 4, and 1. Does this example, this relation here, presented as a table of values, does this relation here show us that y is a function of x? Or can I say for sure that this relation is a function? Well, I have to ask myself the rule. I have to ask myself the rule about the definition of a function, or what I would say is, does each element in the domain, and the domain, of course, is our x's, does each element in the domain correspond with only one element in the range? That would be another way of saying, is this a function, using the definition of a function? Well, let's see. Does each element in the domain correspond with only one? Well, 1 corresponds with 1, 2 corresponds with 4, 3 with 9. -2 also corresponds with 4, just like 2 does. What does that mean? Does that mean this is not a function? No, look at the definition. Each element of the domain corresponds with only one element in the range. It doesn't matter that 2 different elements of the domain, 2 and -2 are 2 different elements, right, correspond to the same element in the range. That's fine. That's fine. But I couldn't have another -2 that corresponded to something different. Of course, -1 also corresponds with 1. -1 also corresponds with 1, but that's fine. -1 is not 1. Those are 2 different elements of the domain that just happen to correspond with the same element in the range. Okay, looks to me like this is still a squaring function that we're looking at. So I would say yes, yes, this is a function. Or I could say yes, y is a function of x. Now how about this next example? Let's see, the domain is the x's, right? Let's put those 1, 2, 3, -2. Oh, 1 is appearing again. Well, do I need to list it again when I'm listing out the set of elements in the domain? No, I don't need it again. It's already there. I don't need to repeat it. There's a domain, the range, 1, 4, 9. I've already got 4, so I don't need to say it again, but I don't have 2. Okay, is y a function of x? Well, let's see. 1 corresponds with 1, 2 with 4, 3 with 9. -2 also corresponds with 4, but that's fine. Functions can do that. But look, 1 is repeated here. Look at this, I've got 1 is here, 1 is here. 1 corresponds with 1, but 1 also corresponds with 2. These are not the same elements in the range. They are not. They are different. So I have to say no, y is not a function of x. And I could say because the element of the domain 1 corresponds with 2 elements in the range. Namely, 1 and 2. Okay, so this one is not, y is not a function of x. not a function. The same element in the domain, 1, corresponds to 2 different elements of the range. So it's a relation that's just fine, but it is not a function. All right. So here we have a function that's being represented as a graph. What's the domain and range of this function? Well, graphical representations are more powerful. They tell us about the entire set of correspondences in this relation, of correspondences between x and y, right? A graph is actually all the possible ordered pairs in a function, right? So if I want to find the domain of this particular function, would I have to list out all the x coordinates of all the possible ordered pairs on that function? That might take me the whole rest of my life, right? Because this arrow is indicating that this goes on forever and ever in the direction of negative infinity, and forever and ever in the direction of positive infinity. So what I really want to say is an interval. I want to use an interval here to identify this domain. I want to use the interval that shows me all those x coordinates, and they can be anything, right? This arrow is saying this goes off forever and ever. It goes up forever and ever, but it also goes off to the left forever and ever, off toward negative infinity. This one does the same thing, up, but also off to the right, towards positive infinity. So the domain of this particular function, then, it has to be negative infinity to positive infinity. There are no limitations on x. I can have any input to this function, or x could take on any value here. Now the range is different though, right? The range, this is all my possible outputs. Where domain is referring to all the x's or inputs, the range is referring to all the possible outputs or all the y's of a function. So the range is going to be all the possible y coordinates of all the points on this graph. Okay, so it's an infinite number here, right? It's going to be an interval again, but it does have a lowest y, or a smallest y. That's a coordinate of a point on this graph, right? Look, this graph never goes into the negative. The y's are all positive. So all the points, the coordinates of all the points on there, here's one right here. This one has the x coordinate of 2, y coordinate of 4, right? This one has an x coordinate of 1 and a y coordinate. Oops, an x coordinate of 1 and a y coordinate of 1. All the points on this graph, all those y coordinates, they're going to be all kinds of positive numbers, but there's no negatives. So I would have to say that the range here, then, the smallest possible y coordinate I could have is sitting right on that x-axis, or the origin, right? Y coordinate at the origin is 0. So my smallest y value here on this graph is going to be 0. There is no largest that goes all the way off to infinity. Now, the thing about the range here that I got to think about is should this be a closed interval or an open interval? Okay, should that actual value of 0 be included in this interval? It should be, because that point 0, 0 is on the graph. So I want to use a square bracket here to indicate that that's a closed, that the left end of that interval, or the negative end, the small end of the range is closed. The 0 does get included there. All right, when we're looking at graphs of functions, or graphs of relations, I should say, there's an easy way to determine whether or not it's a function, and that's by using the vertical line test. The vertical line test, it tells us if it's a function or not. If a vertical line does not intersect the graph in any more than one place, then it would be a function. Okay, if I can imagine any vertical line that does intersect the graph in more than one place, or draw any vertical line over the graph that intersects it in more than one place, then it's not a function. It's not a function. So this graph that we were just looking at, is that a function? Well, can I imagine any vertical line that intersects that graph in more than one place? No, any vertical line that I can imagine and draw on there is going to intersect the graph in only one place. So I would have to say, yes, This is a function that passes the vertical line test. Why does that vertical line test work? Well, remember the definition of a function says that each element of the domain, or each x, can correspond to only one y, right? So if this graph never sort of loops around so that the same x can correspond to a different y, then it must be a function. It must be a function. Let's look at another example. What about this guy? This is a strange looking relation, isn't it? This is actually referred to as a piecewise function. Piecewise function or piecewise relation, if we're not sure if it's a function, right? What's the domain and range of this going to be? It's all broken up, right? But I just need to look and make sure it's going to be an interval because it's a graph, right? I just need to see if there's any real breaks in the interval of possible x values. There's definitely breaks in this graph, but if I follow from left, like smallest to largest, smallest x to largest x, left to right, I've got an arrow over here on the left indicating, right, that goes on forever and ever. So the smallest element of the domain is going to be negative infinity, right? That never stops off to the left. But what's the largest element of the domain, and do I need to break it up into chunks? Well, let's see. If we start at negative infinity and we travel up toward the origin, we're good. All those x's can be represented as an x coordinate of a point on that graph, right? And I keep going. It looks like at x equals 1, the graph stops, right? The graph stops. What about when x is 1.0000001? 1.0000001 is going to occur on this portion of the graph up here. So even though there's a break in the graph, there's no break in the possible x's because it continues right here. As we continue following left to right, it stops, but look, at x equals 2, the graph breaks, but it picks up again right here at 2.0000001, and it keeps on going. Okay, so because no x's are eliminated here, the domain is still negative infinity to positive infinity. Negative infinity, positive infinity. Now, well, how about the range? Well, our smallest y, our lowest point on that graph, our smallest y is still 0, right, at the origin, and it's closed because that point at the origin right there is on the graph. So the smallest would be 0. What's the largest y? I don't even care what's going on over here because look, all the y values are represented on this left-hand side of this graph, and there isn't even a break in that graph, right? All those y, or all those points off to infinity, all those y coordinates can exist there, so there is no upper boundary, and I would say that this range is from 0 to infinity with a closed interval at 0, closed at 0. Now, is this one a function? Does it pass the vertical line test? Can I imagine, sometimes you might hear this referred to as the pencil test, or pen test in my case, but can I imagine a vertical line that intersects this graph in more than one place? I don't think so. What if the vertical line that I'm imagining is this one right here? Does it intersect the graph in 2 places? Nope. It intersects the graph down here in that closed circle, but not up here in that open circle, right? We have the same thing occurring right here. It intersects the graph at that closed circle, but not at that open circle. There's no other potential overlaps there, so I would have to say, yes, this is a function. Yes, this is a function. It passes the vertical line test. Okay. Now, let me ask you a question. What if, let's see, well, nah, we're not doing it. Never mind. That is not that interesting. Okay, let's just move on. All right, let's look at this graph here. What's the domain and range here? All right, domain, that's all my possible x's, or left to right, That's the x-axis here, the horizontal, right? What's my smallest x? My smallest x is kind of hard to see, but my smallest x is occurring right here at -1, and that's a closed circle, right? So -1 is my smallest x value, or my left boundary on the domain. It's a closed circle, so that's a closed interval, and we put a bracket there. Okay, what's my largest x value? Well, let me follow that off. Oh, looks like the graph stops right there, but it stops here with an open circle. An open circle. The coordinates of this point there at that open circle are 3, -5, right? 3, -5. So it looks like we go all the way to 3, but it does stop at 3. Okay, so let's say, but it's an open circle. 3 does not get included, so that interval needs to be open at the upper boundary. Okay, so again, the domain -1 to 3, closed at -1, open at 3. Now, how about the range? With the coordinates of this point, by the way, -1, 3. What about the range here? Is the range going to be the lowest point? Well, the lowest point is clearly here, -5. All right, let me put that in. -5. Open circle, so that's open at that end. So the lowest point, or the smallest y coordinate, is down here at -5. What's the highest? Is it 3? Don't be tricked by that. It's not 3 at all. Look, the highest point on the graph is right here. That's the highest point. The coordinates of that point are 0, 4. So the upper boundary on the range is actually going to be 4. Okay, is it open or closed? Well, is that point on the graph? Sure. So it's going to be closed at the 4. Okay, is this guy a function? Does he pass the vertical line test? Oh, sure. Can't imagine a vertical line that's going to intersect that graph in more than one place. One more example here. Look at this guy. And this is actually an ellipse. What's the domain here? What's the smallest x, or the leftmost portion on the graph? Looks like it's right there. What are the coordinates of that point? Let's see. X is -1, 2, 3. -3. I'll put the y just for thorough, to be thorough. -3, 2. -3. So this looks like the smallest x coordinate, or leftmost portion on this graph, is -3. And that point is definitely on the graph. So let's put a closed interval next to it. So we want to include that point. The largest x, or the rightmost portion of that graph, rightmost point on that graph, I should say, has the coordinates 5, 2. So then the largest x coordinate of a point on this graph is going to be 5. And that point is on the graph, so we want that to be a closed interval. We want to include that value of 5. See, all these other x coordinates in here, those are all points that are on that graph, right? And they all have x coordinates in between -3 and 5. Okay, the range, the smallest at y, or the lowest point on the graph, looks like it's right here. Looks like those coordinates are 1, 0. So the smallest y is 0, and it's on the graph, so that'd be a closed interval. The highest point looks there, would be right there. That has the coordinates 1, 4. So it looks like 4 is the largest y. That point's on the graph, so we'll close that interval as well. All these other points have y coordinates that are in between 0 and 4. Now, is this one a function? No, it's not, right? I can imagine lots of vertical lines that intersect that graph in more than one place. Lots of them. So I'm going to say no. The relation, but it's not a function. It's not a function that does not pass the vertical line test, or each element of the domain does not correspond with only one element in the range. Because, well, if I look at the, let me draw one more line that has coordinates that are whole numbers. If I look at this line here, look, when x is 1, y could be 0, or y could be 4. So with that same element in the domain, that same x, 1, I get 2 different y's. So that cannot be a function. How about this one? Is that a function? Let's say that I'm not showing, but let's put some arrows on it. No, it's not a function, right? Look, I can actually draw a line here that intersects this graph in 3 places. 3 of them, right? So no, not a function. What's this domain? No limits, right? Negative infinity to positive infinity. What about the range? These arrows are indicating off to the left, but they're also going down a little bit too, aren't they? They're also going down, and this side is also going up a little bit. So I don't think there's any limits on the range either. I'll say the range is negative infinity to positive infinity as well. All right. So we can evaluate functions. To evaluate a function, what that means is to find the value of the function for some specific input, right? Or to find the y, the output, that corresponds to some specific x or input. If I'm evaluating a function algebraically, in function notation, I'm going to refer to that function as f of x. That's just function notation for y, right? F of x equals y, or just as function notation for y. So I'm going to, and it's showing me that this is a function called f, and it's accepting x as its input. Okay? The algebraic definition of that function is actually the rule that we use to find the output of that function, or the rule that we apply to x to get y, right? So if I've got this function here, f of x, and it's defined as x squared minus 1, if I want to find f of 3, 3 is being replaced for the x, right? I want to find what output do I get from this function when 3 is the input, right? Or what y will correspond with 3 as an x. So how do I find that? Let's put that 3 right in there. F of 3 is going to be not x squared, but 3 squared minus 1, or 9 minus 1. Oops, 9 minus 1, of course, that's 8. My hand got a little bit ahead of my mouth there, didn't it? Okay, what about f of negative 2? I'll just put negative 2 in there for the x. So that's going to be negative 2 squared minus 1. Now be careful with these negative numbers. Look, I don't want to say negative 2 squared, do I? I want x, negative 2, all of it to be squared, because these are different values, right? Negative 2 squared, it says in parentheses, it says, what's negative 2 times negative 2? Well, that's positive 4, right? And 4 minus 1 is 3. But if I've written it this way without the parentheses, this would have said the negative of 2 squared minus 1, or the negative of 4 minus 1, negative 5. Negative 5. And that's not correct. That's not what we're trying to do here. We have to be very careful with negative numbers always. We want to make sure, especially when we're squaring them, because when you square negative numbers, the negative multiplies away. Okay, so it's 3. There's one last question here. It's saying, what is x when f of x equals 8? Okay, what's that saying? That's saying the f of x, or the output, is 8, or y is 8, right? Could say that was the output is 8. Okay, the output is 8. So what is x? We're looking for the input that gives us an output of 8, right? So what do we want to do here? Well, if f of x equals 8, we're just going to substitute that 8 in there for the f of x. Let's make that substitution, okay? So we're just going to say 8 equals x squared minus 1, and then we want to solve for x, right? So we'll add 1 to both sides. So x squared is 9. Well, I completely solve for x, I need to undo that squaring, so let's take the square root of both sides. So x equals 3. Okay. Now, anybody have a problem with that? Is there another possible solution here? X could also be negative 3, couldn't it? X could also be negative 3. Because what What is negative 3 squared? Positive 9. What is 3 squared? Positive 9. So don't forget, whenever you're taking the square, whenever you're solving and with the square rooting, when taking the square root of a variable, just always remember that the solution could be positive or negative 3. Right? So I might write that out like this. I might say x could be either 3, that's the obvious answer, but x could also be negative 3. I don't want to forget about that negative 3, because negative 3 squared is also 9. Okay, we can evaluate functions when we have them represented graphically as well. Graph is really just a visual representation of that function. I could think about that as like a picture of that relation, right? And it tells me all the ordered pairs that satisfies it. So it tells me, given any x that's in the domain, I can find the y that x corresponds to by simply finding the coordinates of the point on that graph, right? A few of them are marked here. Here's a point on that graph that has the coordinates of negative 1 and 1. The x is negative 1, the y is 1, right? Here's another one, that point has the coordinates 1 and 2. Here's a point down here. What are those coordinates? The coordinates of this point here, x is 3 and y is 0, right? And any other point, I could estimate what they are. Let's see, it's hard to find whole numbers, but maybe, I don't know, if I add that point there, I don't know if that's exactly right, but that might have the coordinates 4, 2. Of course, but I can find, given any x, I can find the y that it corresponds to just by identifying the x and y coordinates of any points on this graph. So if I wanted to evaluate this function from the graph, and I wanted to find what is f of 1, right? Well, I'm sorry, negative 1, f of negative 1 is the x, right? Negative 1 is the x. F of x is just function notation for y. Okay, so what I want to do is I want to find the y that negative 1 corresponds to when it's x, right? So when x is negative 1, there's negative 1 right there. That's corresponding to this point on the graph. When x is negative 1, y is 1. So f of negative 1 equals 1. Okay, the ordered pair, because the ordered pair is negative 1, 1. When x is negative 1, y is 1. What about f of 1? Well, when x is 1, what is y? Well, when x is 1, let's see. When x is 1, that's that point right there. X is 1, y is 2. So f of 1 is going to equal 2. Right? Well, what is f when f of x equals 0? This is saying y equals 0. F of x is function notation for y. When y is 0, looks like we're right here at this point on the graph. That means x is going to be 3. When y is 0, x is 3. Okay, so we can evaluate functions algebraically. We just plug that value for x in and simplify. We can evaluate functions graphically. We just find the point on the graph that is represented by the x that we're looking to evaluate. All right, now let's just switch gears a little bit. Let's talk for a minute about, while we're talking about graphs, let's talk about transformations of graphs. Okay, so if we know the graph of a function, it's usually fairly easily to find graphs of similar functions when we apply the rules of transformations to that function, right? So let's look at this example here. If we have a function f, function is called f, it accepts x as its input. So that function is defined as 2x plus 2, right? Or in words that would say, take an input, multiply it by 2, and then add 2 to that value. Okay, if we were to graph this function, f of x equals 2x plus 2, that's the same as graphing the line, y equals 2x plus 2. If we were to graph that, we would get this black line here. Okay, so there's the graph of f of x plus 2. Now, if I were to add 3 to that function, right, that would mean that each y each y that I evaluated when given an x would be 2x plus 2 plus 3. I'd have to add 3 to each of those y's, right? So I might say that this function is now f of x plus 3, or the definition of that function plus 3, and I might simplify it. And what that does when we add something to a function is it shifts the graph of that function up 3 units, right? So f of x plus 3, or 2x plus 2 plus 3, or 2x plus 5 is this pink line here. This pink line here. Okay, and this pink line is simply shifted up 3 units. It's the black graph shifted up 3 units. It's that original function shifted up 3 units. Okay, so whenever we add something to a function, we're shifting it up. Similarly, when we subtract something from a function, we're shifting it down. We're shifting it down. So if we look at that same graph that we were looking at, 2x plus 2, y equals 2x plus 2, or f of x equals 2x plus 2, there it is, the black one, okay? If I subtract 1 from that function, f of x minus 1, right, if I subtract 1 from that function, it's going to be the 2x plus 2 minus 1, or 2x plus 1. That new graph gets shifted down 1 unit because I'm subtracting 1 from it. And the new graph is here, the pink. That's the graph of f of x minus 1, right? Or 2x plus 1. And what we've done here is we've shifted that whole graph down. Can't really write it in there, it's not a space. We're shifting it down 1 unit. Shifting that whole thing down 1 unit. Purple, the pink graph is our original graph, the black one shifted down 1 unit. Okay, so if we add some value to a function, we shift it up. If we subtract some value to a function, we shift it down. There are other transformations that we can do. We can do horizontal shifts as well. If we add something to the x in a function, or if we add something to the input of a function, we're going to shift that whole function to the left that many units. All right, so our original function, 2x plus 2, here it is, our black guy, 2x plus 2 is our original function. Now, if we add 3 to the x, right? So now we're looking at f of x plus 3. So f of x, we have f of x plus 3. And that would evaluate to 2, or that would simplify to 2 times x plus 3 plus 2. For me, simplify that down to 2x plus 8. Anyway, what that does is that shifts the graph to the, my graph is not correct here, is it? It's going to shift, that's not right. It's going to shift the graph to the left 3 units. 3 units. So it's actually going to be this guy. There we go. That pink one. Okay, and that's shifting left 3 units. Left 3 units. So it's kind of weird, right? You're thinking, well, if I'm adding something to the x, I should be making x bigger, right? You tend to want to think that shifts the graphs to the right. But these horizontal shifts are counterintuitive. Don't go with your intuition here. When we add to the x, we're shifting left. Adding to the x is shifting left. Well, likewise, if we subtract from the x, we're going to be shifting to the right. That makes sense, doesn't it? That makes sense, doesn't it? So if we use our original function, f of x equals 2x plus 2, okay, there he is, here's our black guy. Okay, and we add, we subtract 4, we're going to be shifting that graph to the right 4 units. Okay, to the right 4 units. So, again, this graph is not correct. We're shifting it to the right 4 units. Oh, yes, it is correct. Oh, look, there's a 1, there's a 2, there's a 3. So it is correct. I apologize. I was thinking this was 1 and 2. So it shifts it over here to the right 4 units. Okay, to the right 4 units. So again, it's counterintuitive. When we subtract something from x, we shift to the right. When we add something to x, we shift to the left. So subtract is moving right. Now, were my units? Oh, this graph was correct. Look, I wasn't looking at. I was thinking each square was 1 unit on that. Gotta be careful looking at the labels on your axes. Looking at the labels on your axes. All right. So we can shift towards vertically, we can shift horizontally. We can also reflect a graph. We can also reflect a graph. If we have a function, and here's a more complex function, here we have the graph of f of x equals x cubed plus x squared minus 2x plus 1. That's a cubic function, right? And it looks like this. Let me just see if I can make it. Oh, my pen is running out, isn't it? Time for a new pen. I'll go something like that. There it is. That's the graph. If I were to make that entire function negative, right? So if I made f of x be negative f of x, what I'd be doing is reflecting that entire graph over the x-axis. Here's our x-axis. Here's our y-axis. X-axis, y-axis. So I'm going to reflect that whole graph. I'm making the whole thing negative across the x-axis. So it's going to be this pink guy here. Okay. So negative f of x is, we make that whole function negative. Everything in the parentheses becomes negative. Or if we were to distribute that negative, we would get negative x cubed minus x squared plus 2x minus 1. And that's the reflected graph. That's negative f of x. If f of x is this guy, negative f of x is going to be this guy, the black graph, reflected across the x-axis. It's going to be this pink graph. All right, we can also reflect graphs across the y-axis. So if we make the y negative, and this last one we made it y negative, all the positive y's became negative, all the negative y's become positive. Look, here's the positive y's, now they're negative. Negative y's, now they're positive. Okay, that's a reflection across the x-axis. Well, if we make all the x's negative, right, all the negative x's over here become positive, all the positive x's become negative, then we're reflecting across the y-axis, right? So if we have this graph here, same one, f of x, to get f of negative x, all of our x's become negative, so we're reflecting across this y-axis. Here's our y-axis. I'll draw that in a little darker so you can see that better. Okay. Now our graph is the pink graph that's reflected across the y-axis. So here's our original. If we imagine flipping that over the y-axis or reflecting that, we get the pink graph, right? So look, over here, all my negative x's, this shape on the graph, came over here and became positive. So we have f of negative x. All my positive x's over on this shape in the graph, when I reflected across the vertical axis, they became negative x's over here. Okay, so we can have reflections. Negative f of x is the reflection across the x-axis. F of negative x is reflection across the y-axis. And the way I always remember them is if it's negative f of x, like it was here, negative f of x, right? This f of x is function notation for y. That just means all my y's become negative, right? So that means all my positive y's up here become negative, all my negative y's become positive. It means I got to flip it over the x-axis. Okay, if I'm graphing not x of, or f of negative x, all my x's become negative. So all my negative x's become positive. We flip it, all my positive x's become negative. That's how I remember those. All right, so let's look at an example. Now that we have all these rules, let's look at an example. Do I have a summary of the rules? I'll show you those now. So I have an example. Let's see, given this function f of x, and it's defined as x to the fourth power, find a new function that is the result of a downward shift of 3, a shift to the left of 6, and then a reflection about the x-axis. All right, so we're starting with f of x equals x to the fourth. We'll call this new function g of x. Okay, and it's going to be f of x with all these things going on. Well, what's the first thing? The first thing says it's a downward shift of 3. Downward shift of 3. That's a vertical shift down. That means I need to subtract 3 from the whole function. So here at the end somewhere, it's going to say minus 3. I'm subtracting 3 to get my downward shift. To get the next thing says we have a shift left of 6. Okay. Well, shifting left of 6, moving to left, that means I have to add something to the x, right? So originally it was x to the fourth, but if I'm shifting left, that means add. I'm going to need to, and if I'm shifting left 6, I'm going to need to add 6 to the x. Okay, and then okay, so there's the down shift down 3, shift left 6, and the last thing that's happening is we're reflecting about the x-axis. So if we're reflecting about the x-axis, that means all my positive y's up here are becoming negative down here. So that means my whole function is going to be negative, right? All my y's, all my positive y's are going to become negative. So I'm going to need to stick that negative out front there. I want my whole function to be reflected. All right, so there's that example. Let's look at another one. Okay, here we have a function p that's equal to r of z that's equal to negative the square root of z minus 2 and then plus 3. Okay, and that function was obtained from a linear transformation of the function t of z, which is simply defined as the square root of z. Okay, determine what transformations imposed on t, this function, to get the graph of p, this function. Okay, we're just wanting to identify the transformations that we see here when transforming this simple function square root of z into this new function negative square root of z minus 2 plus 3. All right, well, what do you see happening? There's a negative kind of out front of all the action with the input variable. The input variable is the z here. That's going to mean a reflection, right? That's a reflection, and it's the whole thing getting reflected, or at least this part of it, right? So that means that all my, and it's not, or I can think about it this way, it's not inside there with the independent variable, in this case z, but it's usually x, right? It's not inside there with that, it's outside, so it all is being happening. So then that means all my y's that were positive are becoming negative, negative y's become positive, so this is going to be a reflection across the x-axis, or reflect about the x-axis. So let's just identify this way. Okay, so that's what that negative means, right? Then we've got the square root of z, but look, we're subtracting 2 from all those z's, right? Or we're subtracting 2 from all those independent variables. Those are all the input variables. We're using z here instead of x. So if we're subtracting 2, it's this is going to be a horizontal shift, right? Because it's happening to the z, or to the independent variable, and it's counterintuitive. So if we're subtracting 2, that means we're going to move to the right 2 units. So we'll be shifting right 2 units. All right. And there's one more thing going on here. Okay, so we talked about, the first thing was the negative. Oops. First thing was the negative, and that was reflecting about the x-axis. The second thing we talked about was that we subtracted 2 from the independent variable, That's to shift right 2 units. The last thing that's happening here is we're adding 3. We're adding 3 out at the end, or plus 3. We're adding 3 out at the end. So that last thing that we're going to do is we're going to take this whole thing and add 3 to it, or shift up 3 units. And we add 3, we're shifting up 3 units. Okay, so I've got a nice little summary here of the rules for transformations. Crooked, make it straight. The rules for transformations. When we're doing horizontal shifts, if we add to the x, we're shifting left that many units. If we subtract from the x, we're shifting right that many units. Okay, so adding in there is shifting left, subtracting, shifting right. Okay, if we add at the end, we're shifting up. That's a vertical shift up. So we're not adding to the input variable, we're just adding to the function itself. That's an up. And when we subtract from the function itself, that's a down. Okay. With reflections, when we make the whole function negative, that's like making all the y's negative, so we're reflecting across the x-axis. Okay, when we make x negative, okay, all my positive x's become negative, negative x's become positive, that's a reflection across the y-axis. Okay, and then we're not going to do too much of this in this course, but there can be vertical stretches and compressions and horizontal stretches and compressions as well. If you continue on and take pre-calculus, we'll address those in more detail there. But I did want to give you a full summary of all the transformations. All right, a couple more things I want to teach you in this lecture. I want to discuss some of the characteristics of graphs. If a graph can, or a portion of a graph can be either increasing, decreasing, or constant, right? Linear functions are going to be the same across the entire graph. When the graph of a linear function is increasing, as you move left to right across that graph, it will be going up. Right? Or as the x's increase, the y's also increase. As the x's increase, the y's also increase. So I might say as x increases, y increases. Okay, if a graph is decreasing as you move left to right across that graph, it's going down. Okay, or we could say as x increases, y decreases. Y decreases. Okay. A function can also be constant. And that means as you move from left to right, it doesn't change. It can go up or down. Or we could say as x increases, y stays the same, or y is constant. Okay. So let's look at a couple of examples. If we look at this graph here, where is this graph increasing? Where is this graph decreasing? And if anywhere, where is it constant? Okay, when we're identifying an interval of increase or an interval of decrease, we always refer to the inputs or the x values. The intervals of increase and decrease are always referring to intervals of the independent variable. All right. So for this particular graph, as I move left to right, it looks like it's going up, or as x is increasing, y is increasing all the way until we get to this point right here. Okay. 1, 2, that looks like that's occurring at -2. The coordinates of that point look like -2, 1, 2, 3, 4, 5, 6, -2, 6. Right? So I would say that the interval of increase here, or that this function is, and these are implied arrows down here, is increasing on the interval from -infinity all the way up until x equals -2. Okay? I usually use parentheses for intervals of increase or decrease because, technically right at this value here where the graph changes direction, it's increasing right until it gets to this point, then it's decreasing. At this particular point, I like to say that the function is it's neither increasing nor decreasing. It's a turning point. So I usually use an open interval when I'm identifying functions of or intervals of increase and intervals of decrease. Okay, this function, if it's increasing from negative infinity to -2, then it would be decreasing or going down from -2 to infinity. Okay, what about this function? Here's this piecewise function again. Piecewise function. We study those in more detail in pre-calculus. Where is this function increasing? Well, let's see. As I move left to right, it looks like it's increasing. Put those parts. Let's do the increasing parts peak. Okay. Looks like as x is getting bigger, y is getting bigger. As x is increasing, y is increasing on this portion of the graph here. Not here, but then again on this portion of the graph here. Okay, on the two pink portions. So I would have to say this is increasing from x equals 0 to 1. From x equals 0 to 1. And it's still increasing right at that point. It's an endpoint. You could probably put parentheses or square bracket here. I would accept either. I'll use a square bracket because when I see that full circle, I just sure want a square bracket with it. This is decreasing then. It's going to be decreasing on the yellow interval. So where's the graph going down as we move left to right? The yellow portion here. That's my decreasing portion there. And that's going to be the smallest value. There's an arrow there, so that's negative infinity. My largest x, where it's decreasing, it stops right there at 0, doesn't it? Okay, and this function does have a constant interval, doesn't it? The constant interval, let's highlight that in blue. Looks like here's the constant interval. As x increases, y does not increase at all. So that interval looks like it starts just after 1, okay? But it's open right there, so I'm going to use a parenthesis. It doesn't. The actual value of 1 is on this part of the graph, not up here. Okay, and it stops again right here at 2. I'm going to put a square bracket there to show that that interval is closed at 2. Another characteristic of graphs are extrema. Extrema are the largest value or the smallest value. They're the extreme values of a function, right? The extreme values. The absolute maximum of a function is going to be the highest point on the graph, right? On this graph, it's this point right here. Okay, that's an absolute maximum, the highest point. It has the coordinates x equals 2 and y equals 4. Okay, so the absolute max then for this particular graph occurs at this point, 2, 4. The absolute minimum would be the lowest point on the graph. Would be the lowest point on the graph, and sometimes it's an endpoint because this is just a limited function here. It does not have arrows. It doesn't go on forever. So it looks to me like the lowest point is right there. What are the coordinates of that point? Well, I'm going to have to estimate them, I think. Let's see, if 2 is here, that means 1 would be here, 1.5 would be there. I think it's going to be 1.75 for y. X, let's see, if 1 is there, 0.5. Looks like the x coordinate here is 0.5. It looks like the y coordinate to me is, I think, 1.75. I'm going to estimate it at that. Okay. So the absolute minimum then occurs at 0.5, 1.75. Okay. Now I could have worded this differently. I could have said there's an absolute maximum of 4 because the y value is the function value. So the maximum of this function, the absolute maximum of this function would be 4. And it occurs at x equals 2. I could also say there's an absolute minimum of this function of 1.75, and it occurs at x equals 0.5. Some different ways to word that. Relative extrema, they're kind of the same thing, except they're only they're maximums or minimums relative to the points that are near that extrema on the graph, right? So a relative extrema is one, generally it's going to be one where the graph changes directions here and here, but it might be an endpoint as well. It might be an endpoint as well. For this particular graph, we'll assume some arrows here. So the absolute minimum and the absolute maximum, the minimum is going to be negative infinity and the maximum is going to be positive infinity. Well, that's not that interesting. Sometimes we're interested in relative minima and relative maxima. So this function here has a relative maximum right here, and that's the origin, right? So this coordinates are 0, 0. The minimum, the relative minimum, or a low point, if you will, relative to the points that are near it on the graph, is occurring here. That's at 1, negative 2. 1, negative 2. Okay, so we might say this function has a relative maximum of 0, 0. We might say it has a relative minimum of 1, negative 2. Or we could word that differently. We could say this function has a relative maximum of, and what we're interested in here is the y value, because the y is the output of the function, right? That's the dependent variable. So this function has a relative maximum of, where's the y? 0, and it occurs at x equals 0. Okay, it has a relative minimum of, down here, negative 2, because that's my y, and that occurs at x equals 1. Occurs at x equals 1. Okay, so absolute extrema are the absolute high point and low point on the graph, absolute maximum a high point, absolute minimum a low point. Relative extrema are sometimes more interesting, especially when functions that are not limited, that go off to infinity. Relative extrema are just a maximum relative to the points that are near it on the graph, right? Or a minimum relative to the points that are near it on the graph. All right, let's end the lecture with just a couple of applications. All right, here we have a truck rental company rents a moving truck for 1 day by charging a $39 flat fee, but then 60 cents per mile, 60 cents per mile. All right, write a linear equation that relates the cost in dollars of renting the truck to the number of miles driven, and they want X to be used as the number of miles driven. All right, so what we're doing is here, we're writing a cost function, and it's a function of the number of miles driven. Okay, so we might call that C of X. Cost as a function of X, or cost as a function of the number of miles driven. So the function that we're writing here is a cost function. The independent variable is how many miles are driven with this moving truck. So what is the rule to determine that cost, or how can I write this algebraically? Well, I got to pay 60 cents per mile, and X is the number of miles driven, right? So cost will definitely be 0.60X, right? 60 cents times the number of miles driven. But I also do have this fixed charge of $39, right? I've got that $39 that I have to pay even if I don't drive that truck. So it looks like my cost function here is going to be 0.60X plus the $39 initial fee, right? By the way, if I were graphing this, what would the y-intercept be? 39, right? That's my starting point for this function, or my initial value of the function. Y equals mx plus b, right? M, 60 cents, that's my rate of change, isn't it? If I wrote this in slope-intercept form, y equals mx plus b, right? M, that's my rate of change, that's 60 cents. So this cost goes up by 60 cents every time I drive a mile. B is my y-intercept, or my initial value, my starting point. That's that $39 that I have to pay even if I don't drive the truck. Okay, just a little review there. But the second question says, what is the cost of renting the truck if the truck is driven 110 miles? What does that mean? That means that X is 110. I don't really have room to write this. Oh, I can write over here. So X is not 110. So that what I want to find here is C of 110. I just want to evaluate this cost function when x is 110. Evaluate the cost of driving 110 miles. Well, that's going to be 0.60 times 110 plus that $39 fixed fee, which is $66 plus $39 or $105. Get that right. Shouldn't do these things in my head. Let's make sure. 110. Yeah. All right. How far could that truck be driven if the cost must be less than 150? So the cost, or the C of x, right, has to be less than 150. We want to know the farthest we can drive if we can't spend more than 150. I only have $150 for this moving truck, so I got to make sure I don't drive more than what I can drive for $150. So what would I do? I'm going to substitute that 150 then in for the C of x and then solve for the number of miles. So I'm going to say 150 is equal to 0.60x plus the 39. Solve for x. So we'll subtract that 39 from both sides. So then 111 equals 0.60x, and then I'm going to divide by the 0.60. So the number of miles that I can drive then is 111 divided by 0.6, 185 miles. Okay? A pretty common application here of a linear function. Let's look at one more though. Look at one more. Here we have a company, it's producing very large stuffed animals. Okay, the variable cost is $7 per stuffed animal, and the fixed costs are $25,000. Okay, so when they're producing these stuffed animals, the fixed costs, maybe those represent salaries, they represent rent or mortgage on their facility, maybe the electric and the water and whatever, things that we have to spend the money on, even if they don't produce any stuffed animals. So that's our fixed costs, right? But there's a variable cost that's saying that for each additional stuffed animal that I produce, I have to spend another $7. Maybe these are the materials, the cost for materials for these stuffed animals. Okay, they're going to sell the stuffed animals for $76 each. Okay, so it costs $7 per stuffed animal. They're selling them for $76 each. And there's these fixed costs of $25,000. Right, X is going to be the number of animals produced. Part A says to write the total cost as a function of the number of stuffed animals produced. Okay, so we're going to call this function C, cost, C for cost. It's a function of the number of stuffed animals produced. They want that to be X. So we're going to find C of X, and that's going to equal the initial cost plus the variable cost, right? The initial value, or if I think about it in slope-intercept form, right, or rate of change plus fixed or initial value form, the part that's changing, the cost that's changing, well, I have to pay $7 per stuffed animal produced. So that's going to be that variable portion of that, or the amount that changes, right? But the initial value here, the initial cost, I have to spend the $25,000 just to, open the facility and have people working and get started. So there's my function, my cost function. The revenue function, revenue is always going to be the price that I sell the item for times how many items I'm selling, right? So here, we're selling these stuffed animals for $76 each. So revenue as a function of the number of animals produced is going to be, we'll call it revenue function R, and it's a function of X, the number of stuffed animals produced. And the rule to determine revenue, it's going to be $76 times however many I produce and sell, or 76X. Okay? Now, part D says to write the total profit as a function of the number of stuffed animals produced. Well, what is profit? Okay, profit put it up here. Profit, well, that's the amount of money we get to keep after we pay all the bills, right? So profit is always revenue less any costs, the costs that are incurred to make and sell something, right? Or in function notation, I could say profit as a function, P of X is equal to revenue as a function, or R of X minus cost as a function, or C of X. So P of X equals R of X minus C of X. So if I wanted to write my total profit function for this particular function, if P of X equals R of X minus C of X, then P of X is equal to R of X, that's 76X, minus C of X, that's a parenthesis, 7X plus 25,000. Okay, and I could simplify that a little bit, right? 76X minus 7X is 69X. And then distributing that negative, it's going to be minus the 25,000. So there's my profit function. 69X minus 25,000. Now part D says find the number of stuffed animals which must be produced to break even. What does it mean to break even? Well, if we're breaking even, that means our revenues equals costs, right? Revenue equals costs, or the revenue function equals the cost function. So that's one way of thinking about it. Here's another way of thinking about it. If I'm breaking even, I'm just covering all my costs, that means my profit equals 0. P of X equals 0. My profit's going to be 0. So I could find this by setting my cost function equal to my revenue function solving, or I could just set my profit function equal to 0, right? So that would mean that 69X minus 25,000 equals 0. That's all for X. And they'll tell me how many animals do I need to sell just to hit my break-even point? Because I definitely want to at least get to break even, right? We'll go out of business if our costs are greater than our revenues. All right, so we'll add the 25,000 to both sides. So then 69X is going to equal 25,000, and we'll divide by 69. So X then equals, let's see what that is, 25,000 divided by 69. It's 362.32. Okay, so that's a nice number, but what does X represent here? It's the number of stuffed animals produced. Can I produce 0.32 of an animal? I don't think so. I'm going to have to go ahead and produce one more animal. So I want to round up here because I can't have a portion of a stuffed animal and sell it. I want to round up. So I want to say that I need to produce 363. I need to produce and sell 363 animals, stuffed animals, before I hit my break even. I mean, I'll have a little bit of money there because I can't exactly hit break even, but I won't hit break even if I only sell 362. My costs will still be just a little bit more than my revenues. Okay, that is the lecture for, what are we doing here? Something versus function, relations versus functions.